Recall that regular languages are those that are recognized by finite state automata. Alternatively, they are languages that are accepted by regular expressions. The equivalence of these two characterizations of regular languages is called the Kleene-Rabin-Scott theorem. Now, we've seen that regular languages are quite simple in the sense that their generating functions are always rational functions. However, the converse is not true. Let me give you an example. Look at the language which consists of all words of the form 0 to the n, 1 to the n, where n is a non-negative integer. So concretely, this language consists of the empty word, the word 01, the word 0011, the word 000111, and so on. So there's one word in this language of every even order. And so the generating function of this language is given by 1 plus x squared plus x to the 4, which is just 1 over 1 minus x squared, which is manifestly a rational function. However, it turns out that this language L is not a regular language, and one way to show this is to use a result called the pumping lemma. Let me state the pumping lemma. The statement is a little weird, but the statement is really an artifact of its proof, which is very simple. So let me give the statement. So we'll just call it. All it says is it basically lets you take a word in your language and sort of take a small piece out of it and keep pumping that to get more words in the language. Okay, so if L is a language accepted by an automaton with P states, so some positive integer p, then for every word w in L such that the length of w, the number of letters in w, is greater than or equal to p, there is a factorization. That means you can write w as in the form x, y, z as a concatenation of these three words x, y, and z with the following conditions. So where firstly the length of this x, y is less than or equal to p, and we want y to be a non-empty word, so length of y is greater than 0, and such that x, y to the n, z belongs to L for all positive integers n. So of course x, y, z belongs to L, x, y squared z also belongs to L, x, y cubed z belongs to L, and so on. Why does this, for example, show that this language we looked at earlier is not regular? Well, let me just show you that. So suppose this language L that we have here were in fact accepted by finite state automaton with p states. Then that would mean that I could take the pumping lemma would say that if I take the word 0 raised to p, 1 raised to p. So the length of this word is 2p, which is certainly greater than or equal to p, and the pumping lemma would say that there's a factorization where the length of y is greater than 0 and the length of xy is less than or equal to p. So length of xy greater than p means that y will only consist of zeros because it's in the first part of the word w, which consists entirely of zeros. And length of y greater than 0. So this means that y is of the form 0 raised to r for some positive r. And of course r should be less than p. But then what this means is that w, the pumping lemma says that w y z, x y z will also be in L, but x y z will be of the form 0 raised to p plus r, 1 raised to r. But that's a contradiction. This is not in L because L consists of words where it's the same number of zeros followed by 0 raised to p plus r, 1 raised to p will also be in L. And this is of course a contradiction because L only consists of words where you have the same number of zeros, a certain number of zeros followed by the same number of ones. So the pumping lemma gives an easy sort of standardized argument to show that languages like this are not regular. Let's prove the pumping lemma. So suppose that this language L is accepted by a finite state automaton Q, and say we have a word W equals A1, A2, AL, where L is greater than or equal to P. That's a general word of length L, and let Q0, this is the initial state, Q1, QL minus 1, QL be the states visited by Q on input the word W. So we can visualize it as follows. So we start with the state Q0, and from there we see the letter A1 and we migrate to a state Q1. Then we see a letter A2 and we migrate to a state Q2, and so on. Now the automaton that we have has only P states, whereas this word has length more than P. So what must happen here is the number of states of Q is strictly less than L. There must exist I not equal to J, let's say I less than J between 0 and L, such that Qi equal to Qj. So there must be some state that is visited twice by the finite state automaton. So let's say we go like this until we reach the state Qi, and so this would be just after reading the letter AI, and then we go to Qi plus 1, Qi plus 2, and we come back to Qj, which is equal to Qi. So this will be after reading Aj. Here we have Qj minus 1 and Qi is equal to Qj. And then we maybe move on to our in our automaton to here we read Aj plus 1, we move on to Qj plus 1, and so on all the way up to Qn. So this is the nature of the run of the automaton upon reading the word A. And now the factorization that we want is staring at us. Just take W, the factorization to be x to be just a1 up to ai, y to be ai plus 1 up to aj, and z to be the rest, aj plus 1 up to al. And then you see that if you take w equals w prime equals x y to the n z, what will the automaton do when it sees the word x y to the n z? Well, so when it reads x, it reaches up to the state qi, and then it sees the first letter of y, which is ai plus 1. So it goes to qi plus 1 and it cycles around and comes back to qi after reading the last letter of y. So we are back here, and again you can feed it y, and it will again go down this loop. So you can go, if you feed it x y to the nz, it will execute in more or less the same way as it did with the original word xyz, except that it will go around this loop n times. And therefore, after you read y n times, you go into z, which is aj plus, starts with aj plus 1, and then it will resume the same sequence of nodes, of states that you had for the original word w, and of course it will end up in the same state ql, which must be an acceptance state because w was accepted by the automaton. So this is also accepted by the automaton Q for all n. As I said, the proof of the pumping lemma is really very simple and perhaps simpler than the statement, and now you can see why the statement was formulated in this weird way. You can in fact look at this proof and easily write down a generalization of the pumping lemma. Have to be that you always start with reading your word from the first letter. So let me just write down a slight generalization of the pumping lemma, which has the same proof. Suppose L is accepted by an automaton with P states, then for every word UWV belongs to L such that length of W is greater than or equal to P. We have W has a factorization x, y, z, where the length of x, y is less than or equal to P. Length of y is not equal to 0, and U x y to the n z v belongs to L for all n in P. I leave the, just think about how this more general version of the pumping lemma is still proved by the same for the